Hey everybody, Sam here. We've got some great news to share and also a favor to ask. We're in the running for this year's People's Choice Podcast Awards in both the People's Choice and Technology categories, and we would really appreciate your support. To nominate us, you'll just head over to twimlai.com/nominate, where we've linked to and embedded the nomination form from the award site. There, you'll need to input your information and create a listener nomination account. Once you get to the ballot, just find and select This Week in Machine Learning and AI on the nomination list for both the Adam Curry People's Choice Award and the This Week in Tech Technology category. As you know, we really appreciate each listener and would love to share in this accomplishment with you. Remember, that URL is twimlai.com/nominate. Feel free to hit pause and take a moment to nominate us now. Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, I'm joined by Jason Holmberg, Executive Director and Director of Engineering at WildMe. WildMe's WildBook and WildBook for whale sharks are both open source computer vision based conservation projects that have been compared to a Facebook for wildlife. Jason kicks us off with a really interesting story of how WildBook came to be and its eventual expansion from a focus on whale sharks to include giant manta rays, humpback whales, zebras, and giraffes. Jason and I explore the evolution of these projects' use of computer vision and deep learning, the unique characteristics of the models they're building, and how they're ultimately enabling a new kind of citizen science. Finally, we take a look at a cool new intelligent agent project that Jason is working on, which mines YouTube for wildlife sightings and automatically engages with the relevant individuals and scientists on WildBook's behalf. And now, on to the show. All right, everyone, I am on the line with Jason Holmberg. Jason is the Director of Engineering for WildMe. Jason, welcome to This Week in Machine Learning and AI.
Hey, thanks for having me on.
Jason, why don't you start out by telling us a little bit about your background and how you got involved in ML and AI?
So I have a very unusual background and journey into running an organization that is focused on applying machine learning to wildlife conservation. I am a scuba diver. My background is in chemical engineering and in Arab studies. I did a master's degree at Georgetown. So neither of these would be suggestive of a journey to machine learning, except maybe the scuba diving, because wildlife is an area where we see a lot of application potential for machine learning. But the journey is a little bit interesting in that as I got this Arab studies degree, I found myself living at various times in the Middle East, in Egypt, in Tunisia, in Lebanon. And on one of those opportunities, or one of those trips, I was able to travel down to Djibouti, there in East Africa, which is an amazing melting pot of cultures just sitting there. And I was able to go scuba diving, and I was excited to see the world's biggest fish, the whale shark. There was no guarantee I would see one, and we did this live-aboard sailboat going out to sail and dive amongst the Set Frères Islands, which means 7 brothers. There are coincidentally only 6 islands, so I'm not sure who did the math, but there I was, embedded sort of in a group of French tourists on a sailboat, and in fact I went scuba diving, and as we were coming up, there was a whale shark. Now, whale sharks grow up to 60 feet in length. And this was an 8-foot juvenile, so quite small, but actually that's extremely rare. Most of the whale sharks we see in the wild are about 15 feet and larger. So this was a very rare sighting of this juvenile, and I was just enamored. And the interesting thing about a small whale shark is that I was proportional in size to it. So this animal looked back at me, this giant fish, and we had a moment of just swimming together underwater. It was curious about me. Later in life, I was able to swim with some 40-foot whale sharks in the Galapagos Islands, and interacting with a giant, a leviathan like that, is a very different experience. I'm nothing to a leviathan. I'm just a passing speck of dust in the water column. But this young juvenile sort of gave me the time of day, if you will, and we swam together for a bit, and then it disappeared, and that just sparked something. This was in the spring of 2002. So flash forward, fall of 2002, I decided to go on a whale shark research expedition. And I spent a week down in Baja, California on this small boat as this microlight plane circles overhead, trying to spot the whale shark and call down to us. And the sad story is we saw absolutely no whale sharks while we were baking in the sun for an entire week. But I had the second spark, which is as I sat there in the boat next to this field biologist who's got a spear and a plastic tag that's almost like the somebody's title on their desk, those sliding plastic tags that they might have saying their name and their title. It's about that size, and often it'll have letters and numbers on it indicating the individual that they tagged. So I'm sitting next to this biologist for a full week, nothing to do. And he's got this spear and this tag. And I ask him, what percentage of the time do you, recite this tag you're about to spear on the side of a whale shark? And he said, about 1% of the time. And I said, wait a second, 1%? Because I have an engineering background, and I guarantee you anytime you have a process that's 1% efficient, I can get you to 2, right? Just out of raw curiosity and labor. And that was the second kick in the pants. I happened to have graduated Georgetown with my Arab studies degree, was actually working at a company called Softworks EMC, then EMC, then now it's called Dell EMC. And I was learning to code, and I had all this extra time on my hands. I was young and single. And I started thinking about the pattern of spots on the whale shark. And whale shark can have blue or brownish skin, but it has all these white spots like constellations just rippling across both sides and the top of the animal. And I started thinking about using that as fingerprints. And I wasn't the first person to think of that. It had been theorized, but nobody had actually sort of implemented a pattern recognition system for whale sharks. And here you see the hints of computer vision emerging, right? So this is fall 2002, and I began creating my own, basic trigonometry type spot pattern recognition system, where I would take a photograph and I would map the spots, and I would take those sets of coordinates and have 10 comparison sets in my list, and then my n+1 set of coordinates, and I would try to come up with some complex trigonometry. And really wasn't getting anywhere. By about the 11th or the 12th pattern, my accuracy would just start falling apart. And so I remember working late one night, not on work, but actually on this. It was a Friday night, and I had no plans. And a friend of mine, who we now have a really long-term friendship, he is Dr. Zaven Arzoumanian at NASA Greenbelt. He called me out for a beer. And as some discoveries go, they happen over a beer. And so I sort of dejectedly say, well, yeah, sure, why not? I'm not making any progress here on Friday night. So I go downtown Washington, D.C., and I sit down with Zaven and order a beer. And he has another astronomer with him there coming back from a convention. This is an optical astronomer. And Zaven says, hey, why don't you tell my friend about what you're trying to do with the sharks? I said, well, I'm trying to map the spots on the side of a whale shark and compare the patterns across photographs. And casual as can be, this optical astronomer, whose name I've forgotten at the moment, just turns to me and goes, oh, yeah, we do that. What are you talking about? Hold on a second. What are you talking about? And he said, well, in optical astronomy, we take multiple pictures of the night sky, and we want to create, large composite images. And sure enough, what we need to do is triangulate on different constellations, and that allows us to get key points and create master image sets. And I was just blown away. Mm. And so, he references me to the right papers, and then Zaven really sees that I'm going to put in the effort. And so he sits down as an astronomer to help me. Even though he's a pulsar astronomer, moonlighting in whale shark research is just something you might do at that level, I guess. Right.
I'm not sure I saw the connection coming when you referred to the spot patterns as constellations.
Yeah, exactly. And this just sort of all unfolds in this, amazing way. And so Zaven and I sit down and translate this 1984 arcane paper by, I believe it's Edward Groth, who it turns out also as as these things do sometimes, that Zavin used to play baseball with. But nonetheless, this Edward Groth is a professor who's funded under the Hubble Space Telescope. He develops this algorithm for mapping and comparing star patterns across photographs. And it works. We modify it a little bit. The photographs of the night sky can have, need to be rotationally independent depending on where the observer is, but whale sharks have a top and a bottom. So we make these changes, and voila, we have this highly accurate whale shark spot pattern comparison system. And we can use the patterns on the left and the right side as a pair of tags, like a left and a right thumbprint. So now we have the inklings of an early 2000s computer vision matching system, and one that's actually fairly well defined and proven. Here's the other problem, though. Where do I get all these photographs from? So at this point, I reach out to a biologist named Brad Norman in Western Australia. He had worked for years swimming with the whale sharks that congregate off Exmouth and Coral Bay up in the northwest part of Australia. And it's a really good tourism destination, very reliable place to go and swim with these whale sharks from about, let's say, late March to late July every year. And he'd been collecting these photographs on the off chance that somebody came up with this algorithm. So I blindly reach out to Brad Norman via email, and he responds very skeptically. And I say, hey, I think I might have this, and you might have the other piece, which is the data. And so we begin this long distance collaboration showing that this computer vision system actually worked. And we could reliably, across years, across data sets, across photographs, compare individual whale sharks and determine, without physically tagging the animal, that in fact, years later, this was the same whale shark we might have seen years before. So then we hit what we sort of thought that was the big problem, like creating the pattern recognition system. But what we actually found is there was simply no database content management system for wildlife at all, not even a data model that really could be used out of the box. And so it turns out that 90% of the work was creating the precursors to what we now call WildBook, which is an open source platform to marry good data management, computer vision, and citizen science all together to create a platform for wildlife biologists to collect more data, process it faster, especially in the context of what's called mark recapture. So if you've ever seen the tag on a deer's ear hanging off, or if you've ever seen the band on a bird's foot with a number on it, those are the tags. And for whale sharks, it was the spear and the plastic tag. But those are used to repeatedly identify individuals in a population in what's called mark and recapture studies. And out the other end, you can either get an abundance estimate, how many of these critically endangered animals do we have, or at least a population trajectory. Are their numbers relatively getting bigger or smaller from when we started sampling? And so it turns out that photographic data is now so ubiquitous that harnessing it means that wildlife biologists who tend to still use Microsoft Access and Excel on a daily basis, never mind cloud computing, which is not even a new concept anymore, that they could suddenly have a platform to utilize this much richer source of data. And it turns out it's much better for the animals. We're not physically harming them or getting in the way of their daily life. And so our success applying this to whale sharks, building a cloud platform that allowed citizen scientists, divers, and snorkelers to submit their photographs, the computer vision, which was the carrot that researchers needed to drop their competitive boundaries and begin collaborating for what is a massively migratory fish. All of this just sort of melded nicely into what is now whaleshark.org, the wild book for whale sharks. And whaleshark.org has over 150 researchers and volunteers all over the globe who log in, and about close to 6,000 people from the public have contributed photographs. That model has proved so successful and so cost effective that we've started replicating it for giant manta rays, for humpback whales, and for zebras and giraffes now. And as we started achieving success, that's when a new cadre of researchers showed up. Those researchers are now my co-PIs on the Wild Book project. They're Professor Tanya Berger-Wolf, University of Illinois, Chicago. She's the overall project leader. She does data science. We work with Professor Chuck Stewart, Rensselaer Polytechnic Institute. He has this amazing lab almost exclusively dedicated to wildlife computer vision. And I actually was able to hire one of his students earlier this year. That's another story related to an anonymous Bitcoin millionaire. If you've ever heard of the Pineapple Fund, we can talk about that in a bit. And
I
then,
haven't.
no, it's an interesting story. And then Dr. Dan Rubenstein, professor of ecology at Princeton University. And somehow, and I feel, as I've told you this story, that, how much luck has played. I lucked into a group of 4 collaborative PIs. And at one point, we all just looked at each other, via Skype or whatever mechanism it was at the time. And we said, this is the project of a lifetime. We all sort of nodded. And there's this general sense that funded or not funded, somehow we're just going to get this done. And amazingly, we are now a group of specialists working together. Before it was me sort of trying to hack through a computer vision system and apply the data management. Now we have this wonderful pathway of original research for computer vision done at Rensselaer Polytechnic, advised by Tanya at UIC. And then we transition that over to a software engineering team at WildMe. So at WildMe, as executive director, I manage 4 staff, 1 machine learning expert, Jason Parham, and then 3 software developers, Drew Blunt, John Van Oost, and Colin Kingen, all of whom are 9-to-5 professional software developers working on wildlife conservation. And just the fact that for however long we can afford them, we can afford this dedicated of a team is a giant coup in conservation. I'm just excited at where we are. And if you've ever heard of Microsoft's AI for Earth program, they're investing about $50 million over the next 5 years into applying AI for Earth conservation. We just signed a deal with them, and they are our biggest supporters at the moment. And we're excited about working with them and Azure Cognitive Services and a growing relationship with them as well.
Oh, what a great story. What a great story. You mentioned in there that computer vision started to affect this shift in the academic culture almost within this community to make researchers more collaborative. Can you elaborate on that a little bit?
Sure. So for some animals that don't move very far, it's very cost effective for a researcher to go into the field regularly to observe them, especially if they're located near the animal, and to collect as much data as possible about a population. These researchers can almost do a complete census. Many animals are not like that. They are migratory, especially in the marine environment. They can dive deep and have many unobservable states. And this is where mark or capture modeling, showing up at a field site, observing who's there and who isn't repeatedly, comes into play. But in the marine environment or in remote environments, it's just not cost effective to have a researcher co-located there all the time. Sometimes the animals have migrated away. Sometimes they've simply moved to an area that's remote and difficult to get to. But all of that is extremely expensive, both to support the researcher and to just keep them in the field. With mark or capture, the idea is you show up and subsample the population at certain times. And really, a lot of the marker capture models that are used to estimate these critically endangered or endangered populations are sort of based around human limitations. There's this assumption inside the models as you model capture probability, as you model survival rates to ultimately arrive at abundance or population trajectory, that the amount of time that has passed between your sampling sessions far outweighs the size of your sampling session. So they're not meant for continuous monitoring. And also, research collaborations themselves and the competitiveness in academia really create these silos inside what could be thought of as a master data set. A zebra does not know where the geographic border is, where one research team begins and another ends. Same for a whale shark or a humpback whale as they migrate. We're subsampling data based on really human limitations of funding and time and competitiveness, rather than sort of getting the superset of data, which is what are these animals doing all the time? Where are they? When are they there? Who are they interacting with? What behaviors are they undertaking in these locations? So the idea is how do we push out this human limited data collection into something much more scalable? And that's where citizen science comes in. Can we get a minimum high quality volume of data from citizen scientists, or a minimum quality of good data from citizen scientists, from the public, from people on whale watching boats, from people doing safaris in Kenya? Can their photos be used as data? And that amplifies the data collection of a researcher. Now we start at that point also getting into things like bias, inconsistent effort the data collection and the sampling. But importantly, the largest volume of data that a researcher can get is visual at this point. Everyone's out now in this modern world where we all have cameras, multiple cameras attached to us, especially when we go traveling. That volume of data is sort of yet unharnessed. And especially for animals that are individually identifiable, getting those photos is really getting a data point for researchers. The problem is if you're still in Access and Excel on a desktop and have your photos sort of sitting in folder drives, the flood of data that you can get is far outpaces the ability of a research team to curate it. Let me give you an example. We work with the Sarasota Dolphin Research Project, and they identify individual dolphins, bottlenose dolphins, by taking pictures of their dorsal fin as it pops up out of the surface. So when they have a huge collection of dolphins, thousands of individuals, when they get that N+1 photo, that new photo, and they decide, okay, which dolphin is this? It takes them approximately 9 hours to match that one photo. Similarly, if you go to Cascadia Research Collective in Olympia, Washington, and they maintain this master set of humpback whale imagery, if you stand in the middle of their offices and you look around you in 360-degree view, you see interns looking at images side by side. And so there's a lot of inefficiency in manually reviewing all this visual data that the world can provide. And that, as a sort of long-winded answer to your question, is why computer vision is just so critical. It is a literal time and cost savings to these researchers whose funding just doesn't scale very well.
I guess I'm thinking of the way that computer vision has kind of evolved in this application since your initial models. Clearly, deep learning and convolutional neural nets I'm imagining, are playing a huge role here as they are in other places. I'm wondering particularly if there are any unique characteristics of this type of data that change what you can or what you can't do, or the types of models that you use to identify these specimens.
Sure. And you're absolutely right. The convolutional neural networks are changing this, and that's why our partnership with Rensselaer Polytechnic is so important. The crude algorithm we still use for whale sharks has been replaced for other species. For humpback whales, we use deep convolutional neural networks to identify humpback flukes, the backside, the underside of their tail, if you will, in two different ways. These tools are also proving much more scalable, but let me take a step back here. A lot of times the challenges that I read about in the literature in computer vision are about categorization, right? Maybe identify the species, maybe there's tens of thousands, or more ideally, you're looking at categorizing things. It might be a binary, is this a failed part or a passed part? It might be, put these images into 10 different buckets. The interesting thing about computer vision for wildlife, especially for identifying individuals, is that by nature, we're searching for an individual. We're searching for a needle in a haystack. And let me give you an example of what the problem. So my first attempt at humpback whales and doing a computer vision system, I sat down and started playing with a fairly basic computer vision algorithm. And my first competent pass, I was 99.8% successful in categorizing my photos. And I thought, wait a second, I must be a genius. I must be good at this. This is my calling in life. And then I looked at what the algorithm had produced. And I had created a machine learning agent that predicted false 100% of the time. Because when you have, it cheated. And you know what? It was accurate 99.8% of the time, because when you have one photograph and you're looking through 50,000 photographs for an individual you may have only seen once before, your probability that it's false is almost always 100%. It's so close to 100%. So, applying computer vision to identify individual animals in a field of many, thousands of humpback whales, over 9,000, among 50, 60,000 photographs, it's a needle in a haystack problem. And that's why deep learning is so incredibly important here. I'll give you an example of some of the research that's coming out of RPI that my team is adapting at WildMe. There's a PhD candidate, Hendrik Wiedemann, at Rensselaer Polytechnic. He's creating an algorithm called curve rank, and sort of tying in with that Sarasota dolphin research project. The idea of curve rank is that the edge of a dolphin fin is individually identifiable. Now, previous attempts for edge identification have absolutely occurred. They've used, for example, dynamic time warping as a basic, point pattern matching or line matching algorithm. The problem is that not every bit of that fin is actually indicative of individually identifiable information. In fact, most of it isn't. Most of it's fairly flat and generic. So what's important about Hendrik's work is, given this catalog of multiple photos per marked individual in the dolphin population that the Sarasota Dolphin Research Project provided, he learns which section of the fin contains that individually identifiable information. And that then allows us to only compare those small sections of the fin to give us the ability to, go through that haystack and find that needle.
I guess there have been research efforts around what's called fine-grain classification problems. Are you familiar with that work, and does that apply here, or is it a different formulation of the problem when you're trying to identify the individual? Do you even think of it as a classification problem or something different?
And this may be that I'm somewhat of an outsider coming into the machine learning community. I generally don't think of it as a classification problem. I do have intelligent agent classification problems that I'd like to go into, but in terms of the individual identification, I generally don't think of it as a classification problem.
Okay.
And I don't think for each individual, I don't think we train up an individual classifier, if you will. Although I'm aware of others. Let's see. There's Ben Hughes out of the UK. He's been working on white shark fin identification, and he absolutely builds a classifier per marked individual. So I believe that is more of a traditional classification problem.
Okay. So you alluded to some new work that you're doing to build intelligent agents around Wildbook. Can you talk a little bit about that?
Sure. So I'm building what is, I believe, a combination of a model-based reflex agent and a learning agent to data mine YouTube for wildlife sightings that get missed. And so there's a short story that I'll get into here that describes why I'm going about that. And this is my individual work at WildMe. When being executive director gives me a little bit of breathing room, this is what I like to work on. So flashback to 2014 and 2015, I'm running whaleshark.org, published a couple of papers on marker capture populations off Ningaloo Reef in Western Australia. I've just had children, and I'm most of the time, being a good parent, sitting at home on Friday and Saturday nights, feeling like my contribution to wildlife conservation is sort of falling away to just programming and maintenance. So I really felt like, I can't be in the field right now. My family needs me. I can't be scuba diving, but isn't there some data that I could collect, something that other people generally don't have access to, other researchers in the community? So I started, while watching TV, just surfing YouTube for whale shark videos, and started downloading them, capturing keyframes, mapping the spots on the whale shark, submitting it into Wildbook, running identification. And it turns out that in 2014 and 2015, just doing that, I collected more data than any individual researcher in the field and identified more marked individuals. And that really got me thinking, okay, that's great, except I don't want to keep doing this. This is actually kind of boring. But I'd like to automate this. And so piece by piece, as this Wildbook collaboration evolved, and as Rensselaer Polytechnic trained up a convolutional neural network to detect whale sharks in imagery, then I was able to bring that in and say, okay, if I download all the videos, can you tell me, are there clusters of keyframes with a high enough confidence that we can say there's a whale shark in it? And then as I started canvassing the literature for other things, like, how would I determine based on free-form text in a YouTube video when this video occurred and where it occurred, I started seeing the different machine learning components that were needed, both computer vision and in the natural language processing sphere, that would be needed to replicate my actions. Essentially, I was trying to put myself out of a job with machine learning. Now, it wasn't a paying job, it was just a volunteer gig, but the idea is, is potentially this the new way of working, of building yourself a set of intelligent agents that do work for you as part of your job? And in this case, if we considered my job trying to find whale shark data, then we've absolutely built that. And the way the system works is every night at 10 p.m. on our server, a little agent wakes up and it asks YouTube, tell me everything that's been, or give me a list of videos that have been uploaded in the past 24 hours that are tagged or titled or described with the word whale shark, or in Spanish, tiburón ballena. And we want to expand this to other languages. We then get a list from YouTube back of in JSON of the titles, the tags, and the descriptions. And based on how I historically curated that data from 2014 and 2015, I'm serving as the critic in the learning-based model. It then will make a prediction on true or false. Does this, based on the way the video is described, does it contain a wildlife sighting? And that's important because it's really acting as a very powerful filter, and I retrain it periodically. So as I make decisions, ultimate decisions on what it collects, it then learns on what I said, yeah, that was right, or no, that was wrong, and is able to make better predictions. So it first makes this true false, is this a wildlife sighting of a whale shark? And that's important because the word whale shark will show up in Grand Theft Auto videos, and all kinds of random places you wouldn't expect, right? And also, just things like the Georgia Aquarium has a whale shark. So
it sounds like, though, that you had the foresight to collect all of that descriptive information and your ultimate decision when you first started classifying these videos.
Absolutely. And it's made me really think about, what are the other things in my job that I could start logging now, what decisions I made that eventually I could train machine learning on. Mm-hmm. And because making a prediction, is a very human thing that really cross-applies to machine learning quite well. So this agent makes that initial prediction, and it says, all right, based on how this is tag titled and described, I think this is a whale shark sighting in the wild. And then it goes on to the next step, which is it will then download the video, sample the video every 2 seconds, and then take those keyframes and look for high confidence clusters using a trained convolutional neural network. And we fed data from whaleshark.org in. We did a mechanical Turk process to find the whale shark in the imagery, trained up a detector, and now that detector gives us confidence scores. And if across the video, at least one of the frames rises above a confidence threshold, we then go on. If not, then we leave. And the interaction of the predictor and the computer vision piece is important because, for example, in the vision piece, there's a whale shark somewhere in the world painted on the side of a Chinese airplane, and that video periodically shows up. So we need the vision to find whale sharks, but then we need oftentimes that predictor to throw it out and say, okay, no, we're not describing a whale shark off the Philippines. We're talking about an airplane, so ignore that. So those two interplay quite well and serve as a very strong filter. At this point, once we've gotten past the predictor and computer vision, we're on to thinking, okay, this is probably a whale shark in a YouTube video. And it's at this point that I will take the title, tags, and description and send them up to Azure Cognitive Services and say, all right, do language detection, a pretty common natural language processing task. If any of them are not in English, I will then re-ask Cognitive Services to use neural machine translation, translate back to English. And then we'll take that master string, I'll concatenate all of it, and then I will run a Stanford package called SUTime, which uses named entity recognition to tell me when this occurred. And importantly, I feed in the date that the video was posted, and that contextualizes the description. So if somebody says, I saw this whale shark last week, or if they give a formal date, 2018-06-24, what have you, it's able to resolve that and give me back an ISO 8601 date. Now I know when. So I've got visual confirmation of a whale shark, or high confidence visual confirmation of a whale shark. I know when based on using natural language processing. And then I do some just simple string mining, data mining to figure out the where. Eventually I want to train up machine learning to also detect where, but right now we just look for keywords.
On that when part, to what degree is that a probabilistic determination? If you've got multiple possible dates, or if it's, about a week and a half ago, does it just, does it pick something, or do you get some weighted set of dates? I'm wondering, I guess, where in the process does the final determination of a candidate date happen?
That's a really good point, and definitely an area for improvement. So what we get back out of SUTime is an array of all of the dates and then that are present. And it's not probabilistic. It's anything that it determines it finds. Now, there may be some probability threshold built in internally that I'm not aware of, but it will simply give me a list back of everything it finds. I will then, because it's giving me a standardized format, I will then do my best to take the most detailed date. So it might find last year and say, okay, 2017. It might find, last month, and then it might actually find June 25th, 2008. I will go for the date that contains the most amount of information, including starting with year, then month, then day. But learning which date should be used is actually something that we could train machine learning on, absolutely, and give a probabilistic ranking on that. So it's a really great point. We don't do that. But importantly, if we don't have the where or the when determined, we actually will have the agent post back to YouTube, again, trying to post back in the poster's original language. So we might engage neural machine translation again if we detected Spanish. Ask them the question, when did you see this whale shark, or where and when?
Meaning in the comments?
Yeah.
That's pretty cool.
It is. And then we just added recently the listener that will then asynchronously just pop in occasionally and look for the response. So it's going to look through all the YouTube videos that we've curated, look for those missing date and location, go out and then look for a response, feeding the replies to our comments back through the machine learning to do location and date detection. And then ultimately, in this vein of that we like to call rewarding the gift of data for the gift of knowledge, when a researcher finally approves and says, okay, this is whale shark A001 Stumpy off Ningaloo Reef, when we make that ID of the YouTube-derived data, we post back the link to the Wild book that says, did you know that we found whale shark A001 in your video, and here's a link to everything we know about it. And we have, to our questions, we have about a 45% response rate, which I think in the world of marketing is awesome. But when we ask questions, people do reply. The agent listens for the reply and then tries to inform them of the conclusions we've made based on their data. And the great thing about this is, if we think about citizen science, public participation, there's an upper limit to the number of people who participate that's related to the amount of outreach. How much have we gone out to the public and told them that they can even, contribute data about zebras or giraffes or whale sharks? And then there's a subset of those people who are informed that will choose to participate. And so we're always up against this. Well, not enough people know about this. How do we get the word out, et cetera? The interesting thing about running an intelligent agent this way is it flips that model. We go to where people are already choosing to participate. We show up randomly, curate their data under fair use, and then inform them what we found. And all of that is automated. And so, retraining that agent, improving its quality is always an ongoing mission. But now we're looking to cross-apply that to other species. How do we start doing this for humpback whales and giant mantas, et cetera?
Have you also thought at all about other domains more broadly that you might be able to apply this approach, meaning beyond wildlife conservation?
I've thought about data mining for marketing. I would be surprised if there wasn't a company already doing this, whereby you could monitor social media using a complex interaction of machine learning and intelligent agent, and figure out who is talking about your product, who's having a bad time with it, who's having a good time with it, who are your influencers, et cetera. But the combination of computer vision and natural language processing to really find the product in the imagery, is my product appearing, and then look for sentiment analysis. What are people saying? Is it generally good or bad? Look at the comments. Are those good or bad? And then get a sense of how a product is doing in the marketplace. That struck me as a sort of for-profit cross-application.
This is really interesting. When I think about the traditional AI, a big part of traditional AI, maybe in the 80s or something, was research around this whole idea of intelligent agents, and we'd all have these avatars that, while we sleep are out doing our bidding. This is one of the best examples I've heard thus far of something along those lines. I mean, there probably are others, and maybe folks will, write in and tell me about all the other great examples of this, but it seems like a really interesting approach to, as you say, curate content, but also engage with folks and, pique their curiosity, allow them to contribute to this broad effort without them needing to actively seek it out. It's very cool.
Yeah, and it's a little bit mind bending too. I think about whaleshark.org and how we have something like 152 researchers, and then this one inhuman agent participating in this global study of the world's biggest fish. What does that mean in terms of having autonomous agents collect data and participate? One of the things I want to do is start having the agent not just participate or interact with the public, but interact with the researchers who are logging into WildBook and curating data. The agent absolutely should show up and tell them it found new data from their study sites. And then, what can it analyze? What can it inform them of as part of their experience? We're pretty far from Jarvis and Iron Man, but, we are at least a baby step in that direction.
Right. Very cool. One of the things that you mentioned in the process here is active learning. So kind of correcting this agent periodically and allowing it to update its model, its view of the world. How have you built that into the process? Do you kind of just retrain periodically, or do you have something more sophisticated happening in there?
I retrain periodically. It's basically a dance I do with the agent. So the agent collects data. I will do the finishing curation on it, basically deciding, did you get it right or not? And then that will be a part of the next training set. Mm-hmm. And in the early stages, we're talking about thousands of data points. So I'm using a simple random forest algorithm using trigrams, not especially sophisticated. We're using Weka, the open source package in Java. But there's a lot of room for improvement there. And then especially as the agent, as we get more data and get a little more mature in using this agent, I might allow it to periodically just retrain itself based on my curation. But then ultimately, I want to expand it to the other human researchers participating in the system and their decisions around the data that it collected.
Did you choose Weka based on a preference for Java, or was there some other driver?
My background is through Java. I'm rapidly converting to Python. But as you heard from my story, my route into machine learning is so non-traditional that Weka was a very accessible machine learning tool. It's the algorithms inside of it. These are older techniques, obviously. And for newer techniques, I really value my staff member, Jason Parham, who is just finishing up his PhD, as well as our collaboration with Chuck Stewart, Hendrik Wiedemann over at Rensselaer Polytechnic. They're pushing the boundaries of pattern recognition for wildlife. And then, it's my professional engineering team's job to implement those paper-worthy algorithms as user-worthy software products, essentially. WildBook is open source, but we very much think of it as a product because ultimately these different wildlife biologists who are in the field coming back with photographs of their study populations need to use computer vision successfully. One challenge we have right now, for example, is humpback whales. We actually have two computer vision algorithms that operate in the 75 to 80% success range, identifying the correct whale in the top one, but they have different failure modes. So teaching a field biologist who has no computer vision experience how to interpret two different computer vision ranking results and potentially even boosting those or using an SVM to create a metascore that is interpretable to them is one of the usability challenges we still have ahead of us. Right now, we literally show two lists. Computer vision found this, and the other computer vision algorithm, curve rank, found this. And it's up to them to sort of interpret that. How do we give them more confidence and reduce the amount of interpretation they have to do? And then if you push it forward, I'm really excited about the marriage of statistics with computer vision. A PhD, now professor, former PhD candidate, now professor at Eastern Kentucky University named Amanda Ellis, took some of our whale shark work and said, all right, a human aided by computer vision ultimately decided the IDs of these different whale sharks in these images. What if we took the cloud of photographs, we used the computer vision algorithm to create pairwise scores between every image in the cloud? And what if the whole concept of animal identity was not left to a human being, but it was left to the computer? to find its pathway through the different pairwise relationships and create animal identity within this cloud of photographs and ultimately provide a population estimate with no human curation. And interestingly enough, some of the work that Chuck Stewart's lab has been doing at RPI is related to building the similar data constructs. So I'm trying to put these two groups together because if we have a cloud of photographs and all the pairwise computer vision relationships that have been mined among them, and we're able to pass that over to a statistician, what it means is we could go from years between population estimates for critically endangered species to weeks, which means that we can evaluate conservation strategies for these animals faster, right? Most population papers that come out for a particular population at a study site are generally, 5, 6, 10 years between population estimates. That's just too slow for these animals that are critically endangered and declining rapidly. Mm-hmm. With machine learning, we're able to rapidly reduce that. It's going to be a lot more research, a lot more development effort, but it's just crazy to me how many applications for computer vision and machine learning there are in wildlife research, and how much of that skill set is out there untapped for conservation.
I'm curious, you've mentioned on several occasions citizen science as regards the engagement of, ordinary folks taking pictures, posting them, or maybe labeling things through WildBook. I'm wondering if you if you see a role for the analog among data scientists, as data science and machine learning technologies become more accessible, as the data science community grows and wants to engage in the areas around which they have personal passions. Do you engage with those communities? Do you see roles for them to support projects like this?
Oh, absolutely. I'm really fascinated about new data science techniques for managing an increasing volume of data for wildlife conservation. And Tanya Berger-Wolf, my collaborator at UIC, is investigating this as well. What are the biases in crowdsourced visual data? Can we create population estimates on that are as accurate or better than traditionally collected research data? How big are some of these populations? How can somebody with data science skills help a researcher parse the statistics? How can they help them curate their data in such a way that it's easy to get them into the population modeling packages? Can they come out with the next population model? I really feel like the next generation of conservation tools needs to be driven by data scientists and machine learning experts. It's the only way that wildlife conservation, which is still, so unfortunately done on the desktop, can leap 20 years ahead and catch up to some of the other fields that are using machine learning. It really needs to make that evolutionary leap, and it's going to take data scientists, machine learning experts to help people leap 20 years ahead.
And so if someone who's listening is interested in this area and would like to get involved, how would you recommend they get started?
So, the first place to look is locally. What are some of the wildlife conservation efforts going on locally? And is there a local researcher you can reach out to? I have had and know others who have had the same experience, which is wildlife conservationists, biologists actually tend to really appreciate IT and data experience. I've gotten nothing but warm welcomes when I've reached out to them and said, "Hey, can I help with your data? Can we try to solve a problem for you?" And so, look locally for that. Otherwise, look at WildBook. We are an open source package and would love for contribution. And we can absolutely put you in touch with wildlife biologists who we might not currently have time to work with, but who could use WildBook and might need a new machine learning algorithm for their data. So we'd absolutely love to talk to you.
Awesome. Well, we'll link to WildBook and to WildMe on the show notes page. Before we wrap up, is there anything else that you'd like to share?
No, thanks for the opportunity to talk about the WildBook project, our mission at WildMe, and I really encourage your listeners to apply their skills to help with wildlife conservation. We really need machine learning and data science skills to help out.
Fantastic. Thanks so much, Jason.
Thank you, Sam.
All right, everyone, that's our show for today. For more information on Jason or any of the topics covered in this episode, head over to twimlai.com/talk/166. Don't forget to visit twimlai.com/nominate to cast your vote for us in the People's Choice Podcast Awards. And as always, thanks so much for listening, and catch you next time.